So picking up where we left off last time, we were talking about aqueous solutions, things that are dissolved in water. We talked about the way that solids dissolve in water and their trends. We talked about the way that gases dissolve in water a little bit and their trends with temperature. The trend for solids is that when we increase temperature, the solubility of the solids increases in water, just as a general rule, not as a universal rule. So there are some cases where solubility decreases. However, for gases, it's the opposite trend. As you heat up a liquid, the gases become less soluble in water. And that's actually part of the reason why you get little bubbles before your pasta water starts boiling or your potato water or whatever you're putting in your water. There's little bubbles that form initially, and that's because of solutions of gases, dissolved air and other things in the water bubbling out because the solubility of those gases has decreased. So that's what's happening. It's not that your water is starting to boil, but it is a sign that you're getting close to your water starting to boil. There's another way that the solubility of gases changes in water, and that has to do with pressure. So the solubility of gases depends on pressure. We have Henry's law that tells us information about this. The higher the pressure of a gas above a liquid, the more soluble the gas is in the liquid. Higher pressure forces more of the gas to go into the liquid. Higher pressure forces more of the gas into solution or into the liquid. It causes it to dissolve. So if you increase the pressure, you also increase the solubility. Increase pressure, increase solubility. The opposite is also true. If you decrease pressure, you decrease solubility. A can of soda is pressurized with carbon dioxide. I believe it's about 2 atmospheres. When you open that can of soda, there's that big whoosh, that fizz, and hopefully not a mountain of soda. That's the pressure releasing from the can of soda. And when that happens, it lowers the solubility of the carbon dioxide in the solution, and that's why your fizzy drinks initially bubble a lot. It's because a lot of carbon dioxide is coming out. Your can of soda is supersaturated, and so the bubbles are CO2 leaving your drink. So the bubbles are CO2 leaving the supersaturated with respect to CO2 soda. There are a bunch of ways that we can specify the concentration, how much of a thing is in a solution. One of those ways is mass percent. Mass percent is grams solute per 100 grams solution. The solute is the minority component. Or the solid or the gas. Usually we mean solvent as liquid, regardless of the actual percentages. And solution is solute or solutes plus solvent. It's the whole thing, the whole mixture. A solution with a concentration of 14% by mass contains 14 grams of solute per 100 grams of solution. Here the denominator, this bottom term, is mass of solution. I've written it out as mass solute plus mass solvent. We can calculate mass percent. Let's do that for a salt solution. Our salt solution contains 12.8 grams of sodium chloride and 357.1 milliliters of water. You can generally assume that the density of water is 1 gram per milliliter, meaning that we can just swap those milliliters for grams. We have 357.1 grams of water. Our formula is mass percent equals, we'll just do grams solute over grams solution times 100%. We're always going to times things by 100% if it's a percent. The mass of our solution, the grams of our solution, is going to be the sodium chloride, that's our solute, plus the water. So 12.8 grams sodium chloride plus 357.1 grams H2O. So 369.9 grams. And the grams of solute is just the 12.8 grams sodium chloride. So plugging numbers into our equation, 12.8 grams over 369.9 grams times 100%. Grams cancel. And this is a 3.46% sodium chloride solution. Questions? Great. There are other units that we can use. Parts per 100. There's a whole system of parts per. Parts per 100 is the same as percent. There's also parts per 1,000, which is the same as per mil. You don't need to know that, but sometimes, like if you accidentally hold if you're using your percent key on your phone for some reason, you accidentally hold it too long, you might see that option come up. That's per 1,000. There's also parts per million and parts per billion. Those are numbers that you're likely to see if you're looking at like water quality data for some reason. If you're just curious, how much cadmium is in our water? That's publicly available data that you could look at. And that's a place you'd see it. Also in like pesticide residues, those will often be in the parts per million or parts per billion range. So very small amounts. We can also use mass percent as a conversion factor between mass of the solute, that's what's on top, and mass of the solution, which is on the bottom. And there's a couple ways you can do that. You can write it as a conversion or write it as a fraction. The way that my brain does it, I'll show you. So how much sucrose, so we're looking for sucrose in grams, is contained in a 355 milliliter, 12 ounce regular can size soda containing 11.5% sucrose, and we're going to assume the density of the soda is 1.04 grams per milliliter. Because there's other stuff dissolved in it, it's not exactly pure water. So we are starting with milliliters of soda, we're going to grams sucrose, which is sugar. We're starting with 355 milliliters. How do we convert milliliters to something useful? What do we have that has milliliters in it? There's something on the board that has milliliters in it. Density. Yeah, so density is grams per milliliter. We have milliliters, so if we multiply these two, that would look something like this, 1.04 grams per milliliter. So we'd get grams of soda. We'll go ahead and just get that number. 369.2 grams of soda. The soda is the solution. Maybe it's a solution to being thirsty, but that's probably all it is. So 369.2 grams. Solution, we have this 11.5% sucrose that's in soda, which is our solution. What my brain does, from lots of math classes or whatever, I convert this percent into a fraction, or not a fraction, a decimal form. So that's the same as 0.115. Sucrose per 1 solution. The units here would be grams. This would also be the same as writing 11.5 grams sucrose per 100 grams soda, which is our solution. These are equivalent. So if we multiply by 0.115 with this 369.2 grams, that'll get us our grams of sucrose. If we multiply it by 11.5 grams sucrose, divide by 100 grams of soda, that'll also get our grams of sucrose. So times 0.115 grams sucrose per gram solution. This soda has 42.5 grams of sucrose in it. Just quite a lot of sugar. It's like standard for a soda. Questions about doing that? The other way, an alternate way that you could possibly do this, mass percent equals 100 grams solute over 100 grams solution. You could solve for the grams of solute. So like 11.5 is our percent equals grams solute over grams solution times 100%. You plug in your grams of solution, which was 369.2. We do some rearranging. $369.2 grams solution times 11.5 mass percent. equals grams solute, what we're looking for, times 100%. If we divide both sides by that 100%, it's the same as what we were doing down here. So that would be the other way to do it, like do it completely like it's an algebra question. But the shortcuts are either of these. That's the fast track. Another way that we can specify solution concentration, and this is the one we're going to use more, is molarity. Our little mole friend that comes in proctors or exams, Professor Molarity, that's the same molarity that we're seeing here. So molarity has the symbol capital M. I'm specifying that it's capital M because if you write lowercase m, that is a different thing. So capital M is molarity. And molarity equals moles over liters. The moles is of solute, and the liters is of solution. I'm writing out capital M equals moles over liters because I like to use that as a shortcut. Anytime that we've got capital M, we can just write in moles over liters instead. Or if we've got moles over liters, we can just write in capital M. Those units can get switched out however we want them to. And that's a nice shortcut. This is also one of the equations, density is the other one, where you can use the little triangle thing if you like using the little triangle thing. So like for density, density was mass over volume. So our little triangle thing looks like this. For molarity, it's basically the same idea. We've just swapped out parts of our triangle. So you can also use that here. If you know about it, if you like to use it, if you're not sure about what that is, you can come ask me. I can show you. The molarity is, again, moles of solute, and this is per liter of solution. We're specifying that it's liters of solution because there's another unit, that's the lowercase m, where it's not liters of solution. It's not solution in the bottom, it's solvent. If we want to make a solution of a specific molarity, this might be helpful if you're like preparing something in the kitchen, like you need to make a liter of simple syrup or something, or a certain amount of lemonade. You're going to measure out your ingredients. You're going to take a volumetric flask. A volumetric flask, they're fun, sort of. They're very nice for measuring one specific volume, and they're really bad at literally everything else. They're only good for measuring one volume. So this is the measuring line here. So you would add your solid into a little bit of liquid and stir it around. That's so you've got plenty of room for your solution to get stirred. If you fill it up to the neck part of the flask, it doesn't stir very well, and you're going to spend forever waiting for it to dissolve. So you do your shaking, and then you fill it up to the line. And the fun, but not so fun, but very frustrating part of volumetric flasks is that if you overshoot it a little bit, you get to remake the solution because it's wrong. Ask me why that's frustrating. I've had to do it a lot. Okay, so let's say that we're making up a solution. We just threw some stuff together. We want to calculate the molarity of a solution made by putting 22.4 grams of HCl into a beaker and diluting it up to 1.56 liters. Our equation for molarity is that molarity is moles over liters. The moles part is solute, and the liters is for the solution. The whole thing, everything all added together. Another thing you want to avoid, I'm just thinking of it, for mixing things like this, you always want to fill up to your volume at the end. If you get the 1 liter or whatever volume you want and then you add the solid to it, your volume goes up a little bit because that solid your solute takes up some volume, and then your concentration's off. So you always fill up the volume at the very end. Otherwise, your volumes will be off. Okay, back to the problem. We're on track again. So we're trying to calculate molarity. That means that we need moles of solute, and we need liters of solution. Conveniently, we have liters of solution. That's the 1.56 liters. That's our liters of solution. We do not, however, have moles of solute, but we have grams of solute. Our solute is HCl. How do we get from grams to moles? Molar mass. So we're going to take 22.4 grams HCl. We're going to divide it by the molar mass of HCl. The expectation is that at this point in the class, you're a pro at putting together molar masses. So 36.458 grams per mole. 22.4 divided by that number. We've got 0.614 ... because we've got a bunch of other numbers after that. Moles HCl. Now we have our moles of solute and our liters of solution. We can put them together. So molarity equals 0.614 ... moles HCl over 1.56 liters, since that's our total volume. So our molarity is 0.393 capital M HCl. We would pronounce the M here molar, so 0.393 molar HCl. Another thing that we can do with molarity is use it as a conversion factor between moles of solute and liters of solution. So this is like molar mass. The way that we use it is like molar mass, but with solutions. So a lot of our calculations have been grams to moles to grams, or at least that's one that we've done several times. And we can now do stuff like liters to moles to liters, or molarity to moles to molarity, or other things like that. And molarity would be our conversion factor filling in here to get us between liters and moles, or other things. So we want to determine, just to show this off as an example, how many grams of sucrose are in a 2 liter, 2 liter of, basically 2 liters of 0.781 molar sucrose solution. To get to grams of sucrose, what do we need? What units do we need to get there? What can we turn into grams? Moles. We would want moles of sucrose. We could turn that into grams using molar mass. And we can get to moles with molarity and liters. So 1.95 liters. Remember what I said about molarity being moles over liters, and we can convert those two. So we can swap that capital M out for moles over liters. 0.781 moles per liter. So we multiply those two, and we'll get out moles. And then we can turn that into grams. So we've got 1.52295 moles of sucrose. And we've got 521 grams of sucrose. We multiplied by our molar mass of sucrose that I'm just assuming that you can come up with because we've got the formula. If that's something you're having trouble with, stick around after lab. Come to office hours. Go to see our tutor. All right, one for you to try. How many liters of a 2.25 molar copper sulfate solution, copper 2 sulfate solution, contains 55.8 grams of CuSO4? Remember that molarity is moles over liters. I'll give you some time to give that a shot. Compare notes with your neighbors. All right, do we have any guessers? Any guessers about how many liters? 0.155 liters? Let's find out. So we are trying to look for liters. Liters is at the bottom part of our moles over liters. So to solve for liters here, we'd multiply both sides by liters, divide both sides by molarity, and we would discover that liters equals moles over molarity, if we want to do it with some algebra like that. We've got 2.25 molar. We need to find the number of moles. So we want to turn grams of copper 2 sulfate into moles. So 55.8 grams, we need to divide by our molar mass of copper sulfate. Let's see if I remember all the numbers. I'm getting a number of moles of 0.3495 ... moles copper sulfate. I think that's pretty close. Okay, so then we can plug that in for the moles part, and liters equals 0.3495 ... moles over 2.25 molar, and the units that come out will be liters. We get 0.155 liters copper sulfate solution. Questions? There's also a more like pure dimensional analysis way of doing this. You can convert molarity into moles over liters. And if we have moles, the way that we would get these two to interact with each other, the moles and the moles over liters, we'd have to divide by the 2.25 moles over liters so that the liters goes to the top and then the moles would cancel out. That's, I think, a little bit faster, a tiny bit faster than writing out the equation or using the little pyramid thing, but not for the faint of mental math. So if mental math is your friend and you can do that, awesome. Questions about molarity or concentration? Okay, ion concentrations. So like if we're making a solution and it's got an ionic component in it, we typically report the concentration of a molecular solute as it actually exists in solution. So whatever the concentration is, that's also the concentration of the molecule in solution, so like sucrose. So 2 molar sucrose solution actually means that we've got 2 moles of sucrose per 1 liter of solution, because the sucrose molecule stays intact. It's just a 1-to-1. 1 in the solid, 1 in the solution. However, this does not hold true for all ionic solutes. So for ionic solutes, it reflects the concentration before it is dissolved in solution. I can write a better line than that. Before it's dissolved in solution. So for example, if we have a 1 molar calcium chloride solution, when we dissolve this, calcium chloride is a strong electrolyte, the calcium is going to separate off from the 2 chlorides. So we're going to get 2 chlorides in solution for every 1 calcium chloride. So 2 Cl minus for every 1 CaCl2. And so this is actually 2 molar in terms of its concentration of chloride. Or it should be thereabouts. So multiplying by 2 because of this 2 subscript in the calcium chloride. For the calcium, it's 1 mole per liter, 1 molar, the same as the concentration of the ionic solute before it's dissolved. Questions or confusion about that? It's a small piece of stoichiometry just based on the formula. This will become more important when we get to acids and bases stuff. All right, determine the molar concentrations of both calcium and chloride in a 1.25 molar calcium chloride solution. I'll give you a small amount of time. Try to work that out. Compare notes with your neighbors. All right, so we're trying to find molar, that's the capital M, concentrations of calcium and chloride. So we're looking for 2 numbers. So for our calcium and for our chloride. We're starting with 1.25 molar calcium chloride solution. The 2 important pieces of information are the subscripts. For calcium, it's an implied 1. For chloride, it's an explicit 2. So 1.25 molar is our starting point for both of these. (1.25 molar calcium chloride). How many calciums do we have in calcium chloride? 1. So our conversion for the calcium, 1 calcium ion per 1 calcium chloride. It's a 1-to-1 ratio. It's going to be the same thing. So this solution is 1.25 molar calcium ion. How many chlorides do we have in 1 calcium chloride? We have 2 because of this subscript 2. So 2 Cl minus for every 1 CaCl2. And so our concentration is 2.50 molar Cl minus. So 2.5 molar chloride concentration. This is another place where if you can just look at it, you see 1, you see 2, you see whatever the number is, and you do the multiplication, write down what you're multiplying. But if you can basically just do that in your head, that's awesome, go for it. You don't necessarily have to write it out every time. Questions? We're going to be using these tools in our next 2 upcoming labs after the break. So it's very important. Also, you know, it's going to show up on our exam 4. All right, solution dilution. We are going to learn in this section a formula, an equation. That equation is good for solution dilution calculation. So if we want to take a small amount of one solution, add liquid to it to make it a bigger amount of solution, but more dilute, we can use it for that. That's the only thing that we can use it for. That's the only thing that I'll let you use it for. Do not use it for anything else because it will be wrong. Even if it's technically correct, if I see you using the solution dilution equation for something that's not dilution, I will just not give you points for it. So don't do it. This is my hill I'll die on sort of thing for the class. Okay, the reason that we're talking about solution dilution is because if you end up doing chemistry stuff, oftentimes our solutions are stored in concentrated forms. We would call these stock solutions, and those are stored in the stock room where we store our stock solutions. The reason that we do this is it's easier to store highly concentrated small amounts of solution and dilute it down from there. It's easy to just add water or add, you know, whatever solvent to something and make it more dilute. It's really difficult to remove the solvent to make something more concentrated. That takes a lot of effort. So much easier to dilute than to concentrate. Sometimes it's almost impossible to concentrate. There's just too much going on in the world. We've got dogs and cats to think about. There's funny animal images to look at. Funny monkey gif. There's all sorts of stuff going on in the world. And on top of that, all sorts of other stuff, I'm sure. My brain, see, I can't even concentrate. Okay, so to determine how much of the stock solution to use this dilution equation. This is a great equation for dilution. It works for diluting, and that's all it works for, and don't use it for anything other than diluting. Only for diluting. I don't want to see you throwing C's or N's or other things into this equation. Don't do it. Only use this one for diluting. So that capital M is molarity, the capital V is our volume. Molarity is moles over liters, liters being a unit of volume. So if we multiply that by, so if we take moles over liters and we multiply that by liters, what's left is moles. So all that we're saying with this equation is the moles that we started with is the same as the moles we ended with. And that's true because we've just separated things out. We've diluted our solution, but we haven't changed the amount of moles that are in there. It's nothing fancy, but it works really nicely for doing dilutions. That's why it works. Let's see how it works. Let's see it in action coming up here. Again, this applies only to solution dilution. Do not use this for stoichiometry because you'll get it wrong, or I'll just give you no points even if it's right, because I don't want you to use this for stoichiometry. It's a bad habit. We're not going to form that habit if I can help it. Another lab safety note, if you're diluting acids, the correct way to do that dilution is to add the acid to the water. The fun, helpful phrase is acid to water, like you ought to. Acid to water like you oughter. I don't know why that's the fun, helpful phrase, but that's the correct way to do things. Add the acid to the water. When acid mixes with water, sometimes it releases a lot of heat. And if you add water to a bunch of concentrated acid, the acid is the part that releases a lot of heat. And if it releases enough heat, then it releases acid vapors, acid gas, that you can then breathe in, and it'll condense in your lungs, and then you have acid in your lungs. And that's worse than having water in your lungs, which is how you get like whatever that one that starts with a T is. But acid in your lungs is especially bad, so we don't want to do that. It could also explode, and then you've got acid all over your body, and then you get to take a safety shower. We don't really do this. The only time that we do this is in the lab that we're doing this week, but we're not diluting it. So acid to water like you oughter. And let's see this in action, this dilution equation. Our beautiful M1V1 equals M2V2 dilution and only dilution equation. How much, so we're looking for much, whatever much is, a volume. How much 6 molar sodium nitrate solution should you use to make 0.442 liters of a 1.2 molar sodium nitrate solution? This is very similar to the P1V1 equals P2V2 and the other simple gas laws that we have done. The big part is that we want to make sure that we don't get our things mixed up. We don't want to get our state 1 and our state 2 mixed up. So we've got 2 molarities. Let's just call them in the order that they show up. So I'm going to call M1 6 molar. I'm going to call M2 1.2 molar. It doesn't matter which one's 1 or 2. The important thing is that we don't get them mixed up. We have a volume. Our volume is 0.442 liters. Is that volume going to be paired with 6 molar or 1.2 molar? It goes with the 1.2 molar. The of a 0.442 liters of a 1.2 molar sodium nitrate solution. That means those are paired together. Usually the numbers show up together. So this is V2, it pairs with the 1.2 molar. That means we're looking for V1, just the way that I've numbered things. So M1V1 equals M2V2. We can turn that into V1 by itself. Doing that in this top right corner. Divide both sides by M1. So M2 V2 over M1 will get us V1. So 1.2 molar times 0.442 liters divided by 6.0 molar. The molars cancel. We're left with units of liters. And the answer, 0.088 liters. Questions about how we did that? Confusion about how we did that? Okay. This is just a visual of what that might look like. So we would take in our example, this was the volume of our 6 molar sodium nitrate solution. So we would take 0.088 liters, 88 milliliters, add that to a flask. It wouldn't work for a volumetric flask because they have single calibration marks on the neck or stem. But we would add our volume in and then add solution until we get up to the volume that we want to get to. And then, give it a little stir probably right before we get there. And the goal being to just hit that one mark on the neck. If you'd like to see a volumetric flask, I'm happy to pull one out. I can show you during lab. They're pretty cool. They're very accurate. They're incredibly accurate for only one volume, and they're terrible at everything else. So if you're measuring one volume a lot, awesome. Okay, solution stoichiometry. So we're doing stoichiometry stuff. We're doing ratio stuff with solutions instead of with like grams of stuff as our starting end. And we're also not doing like volumes, like liters of gases, because we've also done gas stoichiometry, solution stoichiometry. So if we have aqueous reactants and products, we're often going to know volume of the solution, like in liters, and concentration, like in molarity, of our two solutions. So it's convenient to use those units. It's not convenient to try to figure out how many grams of our solutes we have, or how many, like grams are just really inconvenient for doing these things, because you need density, and you have to empirically determine the density, and that's a whole thing. And so if we know the concentration and we know the volume, we can get moles, and from moles we can do our stoichiometry with our balanced equation. And so our general solution map for these types of calculations looks like this. This is one I showed you before. So we'll start with the volume of a solution. We can use the molar concentration, the molarity, to get to moles. We use a molar ratio from our balanced chemical equation, 1 to 1, 2 to 2, 2 to 1, 1 to 2, 1 to 3, 1 to 2. I listed one of those twice, but you get the idea. And then that can convert us into moles of solution B or moles of chemical B, and then use our molarity of that to get to the volume of solution B. So let's see that in action. The word problems also get more complicated, potentially. What volume? So we're looking for volume. What volume in liters of, key connecting word of, 0.500 molar sodium sulfate will react with 275 milliliters of that molarity barium chloride to completely precipitate all barium in the solution given the balanced chemical equation. Where do we start? Or where do we end? We're looking for volume of sodium sulfate. So we're looking for liters sodium sulfate. How could we get to liters of sodium sulfate? From moles of sodium sulfate. And what would we use to do that step? Molarity. We can use molarity to convert between moles and liters. How would we get to moles of sodium sulfate? What is it reacting with? This is not the right chemical equation. That's fun. All right, let me rewrite this. What a fun goof, huh? Barium chloride. Those are going to make barium sulfate and 2 sodium chloride. Okay, now it's done. It's balanced. I think that's balanced. Yeah, we're chilling. Okay, now that we have our actual balanced equation, what could we use to get moles of sodium sulfate? Moles of barium chloride. We have barium chloride, some numbers related to barium chloride given to us. So maybe it's barium chloride, maybe it's Maybelline. And we could do that conversion using the ratio from the balanced chemical equation. In this case, it's 1:1. And we could get to moles of barium chloride using our molarity and our volume of barium chloride, liters of barium chloride. As a general rule of thumb, for this type of problem, we're going to start with the thing that we've got 2 numbers for. Right, we've got 275 milliliters and a concentration for barium chloride. We only have one thing for the sodium sulfate. We're looking for the other thing. So we're going to start with the milliliters. We're going to start with the molarity. I like to start with milliliters. Milliliters. There we go. So 275 milliliters. How many liters is that? 0.275 liters barium chloride. The reason that I like to start with volume is just 1 unit. Molarity looks like it's just 1 unit. Secretly, it's 2 units in a trench coat. Molarity is moles over liters. And since it's moles over liters, we can multiply our molarity by our liters, and that will give us moles. So that'll give us our moles of barium chloride. And then our ratio of 1:1, nothing changes except our chemical. So the barium chloride gets canceled out. We've got moles of sodium sulfate. I'll just go ahead and get that number for us. So 0.0686875 moles sodium sulfate. How can we go from moles to liters with molarity? Do we multiply or divide by our molarity? Any ideas? We divide. So 0.06875 moles Na2SO4 divide by our molarity, since it's moles over liters. Or the other way we could figure it out, we're looking for liters, do our little triangle method, pyramid method. So if we're looking for liters, it's moles divided by molarity. That's what we're doing here. And so we're looking for 0.138 liters Na2SO4, sodium sulfate. That's the amount of our solution, the amount of this sodium sulfate that we would react to get all of the barium chloride out as barium sulfate, assuming everything goes perfectly well and everything dissolves perfectly. Questions about that? I am now going to show you forbidden math. This is illegal. You remember that equation, the one that we can only use for solution dilution? Let's see what happens if we try using this here. The results might surprise you. So let's say that we've got V1, M1, V2, M2 just to label stuff. So we're looking for our V1. V1 is M2, big M, big M2, V2 over M1. Our M2 and our V2 are 0.250 molar and 0.275 liters, and our M1 is 0.500 molar. The molars cancel. And we get 0.138 liters. It's the same answer. But I thought we weren't supposed to use that. You're not. This is why it's devious. This is why this is devious, is because it will work for some of the problems, and then when you need it to work most, it will fail you, because I'll have set the problem up so that it will fail you. So don't use it. It will work sometimes, but the times that it won't work, like on our lab practical, will get you in trouble. So don't use it. Let's see if we can do that here. Yes, this is one where it won't work. I'll give you a little bit of time. We'll spend the rest of the class working on this problem. A 25 milliliter sample of nitric acid solution requires 35.7 milliliters of that concentration of barium hydroxide to completely react. What's the concentration of the nitric acid solution? I'm going to give you the balanced chemical equation. Also potentially helpful, molarity equals moles over liters. That's one that I'd recommend having memorized. just because it's very helpful for solutions. All right, we've got two chemicals that were given to us in this problem. We've got nitric acid, HNO3, and barium hydroxide. To figure out where to start, the general rule of thumb, if we've got two numbers for it, we can start there. Which one of these do we have two numbers for? The barium hydroxide. So we're going to be starting with barium hydroxide. And I like to start with volume. So I'm going to choose to start with 35.7 milliliters barium hydroxide. Strictly speaking, you don't have to start with milliliters. You could also start with molarity. It works out exactly the same way, thanks to the way that math works. And we are trying to find concentration of the nitric acid solution, the concentration being molarity. So our goal is to get to molarity of HNO3. So how many moles of barium hydroxide do we have? We've got a molarity, we've got a volume. It might be helpful to convert our milliliters into liters. So we've got 0.0357 liters of barium hydroxide. Looks kind of like bacon, but maybe I'm just hungry. So liters, we can multiply that by molarity, since molarity is secretly moles over liters. So multiplying by 0.1508 moles per liter. The liters cancel out, and this gives us the number of moles of barium hydroxide that we have. So 0.00538 ... moles barium hydroxide. Barium hydroxide identified here with that red underline. And what's the other thing that we care about? What's the other chemical that we have? HNO3, nitric acid. Right, that's the other thing that we care about. We've got a number for nitric acid as well. We've got 25 milliliters for nitric acid. So that's the other thing that we care about. And we're trying to get to a molarity, a concentration of nitric acid. So we're going to be converting to nitric acid. So our ratio, this is the solution stoichiometry, or the stoichiometry part of solution stoichiometry. 1 barium hydroxide reacts with 2 nitric acids. So copying and pasting, our ratio is 2 HNO3 gets used up for every 1 barium hydroxide that we have. That's the stoichiometry part. And this will give us moles HNO3. 0.0107 ... moles nitric acid. Questions so far about our journey? Great. We're trying to get concentration in molarity. We've got moles. How do we get from moles to molarity? What do we do? Yeah, it's moles over liters. So we need to divide by liters. We were given milliliters up here in the top left. So converting that to liters, it's 0.0250 liters. So 0.0250 liters, this will transform into molarity, and that's 0.431 molar nitric acid, HNO3. questions about that? There is another trick that we can use here. So I converted both of our milliliters to liters. If you leave the milli on, then we'll have milliliters to start with. And then the milliliters at the end will cancel out that milli. So that's an option for those of you that are not scared of doing a little bit of extra work. I'd also like to show you before you finish packing up, if we do the M1V1 equals M2V2 for this. So show you that it will give you the wrong answer. We would be finding, call it M1 here. So we're looking at M2V2 over not M1V1, where this is our V1, we've got our V2, we've got our M2. So 0.1508 molar times 35.7 milliliters over 25.0 milliliters. The milliliters cancel, so we don't need to convert them from milli. 0.1508 times 35.7 divided by 25. This would give us an answer, an incorrect answer of 0.215 molar. So the stoichiometry part is what throws off using M1V1 equals M2V2. That's part of why I tell you don't use it, because usually people that use M1V1 equals M2V2 don't take into consideration that it won't work in these circumstances. So it's easier to just say don't use it at all unless we're doing dilution. And that's all.